Welcome everyone to the next edition of QRST. And today we have Manuel and Junio. And Manuel is here on my left. And Manuel is working as quantum research scientist at Zapata. And he is at Quantum AI team. He graduated in physics and is very interested in topics such as quantum machine learning and visualization and optimization. And this is something that we'll hear about more today. So Manuel, if you could enlighten us with some of beautiful plots that you created in the last couple of months, that would be great.
Thank you for the very correct introduction. So, right, I assume everyone can see everything just fine. So, yeah, thank you for the invitation. I've attended QRST quite some times and watched videos online. I'm happy to talk here for the first time. I'm actually presenting our recent work around the open source Python library ORQVIZ, which is a Python library for visualizing high-dimensional parameter landscapes, and also the accompanying paper, in which we showcased all the collected visualization techniques that you can actually use with ORQVIZ, with the library, and apply those visualization techniques to a range of variational quantum algorithm examples to showcase how you could approach any research topic or different research topics in the domain of variational quantum algorithms from the perspective of visualizing these high-dimensional parameterized landscapes. Right, so this is a recent work coming out of Zapata with great colleagues, Dylan, Assad, Michal, Luis, and Alejandro, as well as external collaborators, Eric Ansatz, who spoke here a couple of weeks ago, and Jared McLean. And yeah, so we are on the archive with a paper, and you can also use pip install for ORQVIZ, as well as check out the GitHub repo down here for examples, tutorials, and anything. We're very happy for feedback and user experience. So what is visualization? Right, so in visualization, we start off with a high-dimensional parameter space. That's kind of our first thing. So high-dimensional parameter space, every point in that space is essentially mapped by a quantum circuit, because we have a parameterized quantum circuit. We put the parameters and it's mapped to a quantum state. And we can, that the quantum state is then used for any kind of machine learning task, optimization task, chemistry task, whatever, right? But we'll have this mapping between high-dimensional parameter space and some quantum state, right? And so what is visualization? Visualization is actually refers to finding a low-dimensional parameter manifold, a slice in that parameter space, which we can then kind of discretize, because every point on that slice is a parameter vector. Discretize and then evaluate in a function. Right? That function could, for example, be the training loss, right? So we take a parameter vector, put it in the parameterized quantum circuit, evaluate the parameterized quantum circuit, and evaluate the loss function. A lot of kind of sequential things happening, but essentially it's mapped from parameter space to the function. Now, the function could be any scalar function. It takes parameter vectors and gives us a real number. For training loss is a very typical example, right? Where you would get started visualizing whatever. Another thing could be cross-evaluation. So you're looking for a metric which you are explicitly training for, but you want to see its behavior over kind of training progress or in the landscape of the parameter space anyway. Another thing could be fidelity known to a known ground state. Another thing could be like gradient magnitude, right? Like as long as it's a real number, you could kind of evaluate it on this lower dimensional manifold, either a line or a plane typically. It has to be low dimensional because we're humans, right? Like to be able to see it, we need to needs to be that dimensional. And so ORQVIZ is actually a function that wraps a lot of the annoyances that come up when you try to visualize that. So when you try to have kind of high-dimensional linear algebra, as well as projections, as well as kind of matrix indexing, there's a lot of stuff that needs to be kind of fixed in stone and not just work, right? And so ORQVIZ does all of that with seamless functions like perform 2D scan, and where you give it like an origin point function, here for example loss function, then these direction vectors x and y, which span this kind of manifold, a certain resolution, as like how densely do you want to measure the function, and then it will just give you the result. You can directly plot it. Now that's, so ORQVIZ wraps a lot of these things, makes it stable and reproducible and all these things. And it also provides you with a couple of more sophisticated techniques to actually choose a parameter manifold. Because if you have a high dimensional space, you're probably going to run into is that you need to find kind of a good slice, like a good low dimensional slice to the space that actually means something, that actually shows. Well, it depends on your question. Sometimes even a random slice can be good for the research that you are doing, and actually also a good example of ours. But usually you need to find a meaningful direction. And ORQVIZ gives you 3 main techniques on your hands that you can use. And those are actually principal component analysis, PCA, Hessians, and the natural elastic band algorithm. Right? So these are 3 algorithms that help you choose a direction, help you choose a manifold, which is scanning. So principal component analysis, PCA, is a linear algorithm for dimensionality reduction. It's kind of the high dimensional equivalent of casting a shadow from high dimensional space onto like a 2D plane, for example. So if you have a bunch of optimization trajectories and some of like an optimization runs, some of them seem to converge in terms of your energy and VQE, and some of them don't, well, anyway, you will have kind of a collection of points which represent this trajectory in parameter space, high dimensional parameter space. And so what PCA gives you is kind of the 2D plane, which is most representative of the kind of variance of the differences between the points. Is most representative for the entire points as a linear algorithm. So it chooses the plane that actually fits well through your points, and you can, from a collection of points, then make a PCA scan where you scan the loss landscape, for example, which is representative for the actual optimization process. So we will see how flexible they are. Now, Hessians are the matrix of second partial derivatives. Now that means like of your function, of your loss function, for example. That means for a four-dimensional parameter space with a model with 4 parameters, it's a 4x4 matrix. And also it has 4 eigenvalues and 4 eigenvectors corresponding. Now, with the Hessian, a given point that you evaluate a given point, you can essentially then choose, for example, the lowest eigenvalues and their corresponding eigenvectors to create a scan which is very, very low in curvature. Whereas if you choose the highest eigenvalues and their corresponding eigenvectors, you can essentially choose to scan in directions which have very high curvature. Right? And so you essentially, through the Hessian eigenvalues, which are kind of which you can see and which are essentially given to you, you can choose the directions accordingly to have very low, very high curvature in your mix between the scanning eigenvectors. And the natural elastic band algorithm is actually pretty complicated to code up. It's a pretty sophisticated algorithm that finds a finds a low energy path, low loss path in between 2 points, right? So for example, if I have here a cable and I hold it in my hands, I don't pull it tightly, what it does is it slopes down, right? It slopes down because it follows the gradient of the gravitational field, right? And so the same you do with the natural elastic band algorithm, where it models kind of a elastic band which slopes according to the gradient of the function. So for example, the gradient of loss function. And here we're doing a loss, for example, here we're doing a PCA scan on this kind of deformed nonlinear, but piecewise linear natural elastic band that actually found that these 2 points, which came from initial optimization, are not actually disconnected by this high loss path, which is what linear interpolation would indicate, but actually a nonlinear path shows that it's actually pretty low loss. So these are 3 techniques, 3 algorithms that you can use that are seamlessly integrated in ORQVIZ together with all the other wrappers and plotting functions, and that you can use flexibly for your particular application. And yeah, so these applications, we are essentially, we'll give you a brief overview because there is a lot of stuff we could discuss here, but I'm going to try to make it short. We studied in the paper 4 different stories, right? So we said we want to show to the people that if you just have to, you can use visualization techniques in ORQVIZ in a range of applications with any framework whatsoever. You just kind of need an idea of what your research project is, and then you frame it from the perspective of visualization. And so that those are parameter concentration in QAOA, data dependence and generalization in QCBM, it's a generative model, Ansatz Comparison in VQE, and also generally stochastic optimization and shot noise across algorithms. And so I'm going to give you a brief overview of what we were able to visualize. So QAOA, the quantum approximate optimization algorithm, is a quantum algorithm for solving binary combinatorial optimization problems that can be mapped to a diagonal Hamiltonian, such as this one, which we call the cost Hamiltonian. The goal is to prepare the ground state or approximate ground state of that Hamiltonian, because that can then be mapped back to the original problem because it's a good solution to the problem. And the ground state, in fact, is a perfect solution to the problem. And those combinatorial optimization problems are usually represented in graphs, can be represented in graphs where you have nodes, here ij, with edges between the nodes, and that have weights w up here. Right? And so this is, for example, a max cut cost Hamiltonian. Max cut meaning you want to split kind of the graph into 2 partitions, maximizing the sum over the weights that we cut. And so QAOA is this alternating operator ansatz where you evolve an initial state alternatingly under the actual cost Hamiltonian, and then a so-called mixed Hamiltonian, which doesn't commute with the cost Hamiltonian, and it usually the common choice would be just to have Pauli X rotations. And so you kind of repeat these blocks in your ansatz, making it deeper, more expressive, but you have to realize that not each qubit gate is parameterized, but the entire block has a single parameter. So actually the number of qubits doesn't affect the number of parameters, just how deep you make the circuit. And so that gives you this very interesting opportunity, which actually also then is in context of parameter concentration, that you can solve a smaller graph. That was like a super interesting observation, solve a smaller graph, move the same parameters to a larger graph, which has a typical similar structure, and it's also a good solution there. And so this is super promising for initialization strategy. And not just that, but also if you have like maxima, they stay maxima, of typical random bias in between, they stay random bias in between. So we interpret that as meaning the shapes of the loss landscapes are the same, like between smaller graphs and larger graphs of the same type, right? And with the same kind of rules. And so we kind of replicated their experiment visually, starting from a random initialization. We found the corresponding nearest local maximum and local minimum with gradient descent for unweighted and weighted graphs, 3 regular graphs, meaning each node is connected to exactly 3 other nodes. And we did that on 10 qubits. And then we moved it down, we moved it up, just to see what happens. Right? Because we expect the shapes to be the same. We kind of fix the direction vectors with we look, right? And so kind of we fixed the window into the landscape, just moved across the different landscapes, and we saw they all look very, very similar. like like you wouldn't believe me that this isn't, this is actually different graphs, and they all look like that. And so this is kind of parameter, like this parameter concentration demonstrated visually. Like this is, in my opinion, and this is how it should be like explained to people, that the shapes of the landscapes are the same. And visualization techniques obviously reveal that. And because it's so simple to kind of check, we did that on different graph instances as well. So not just max cut, but also the graph partitioning problem, and not just 3 regular graphs, but also heterogeneous graphs where you have random probabilities for your weights in the graph. And yeah, everywhere we demonstrated parameter concentration. And I'm not aware of kind of theoretical or numerical results indicating this. And the reason is probably because the actual minima and maxima don't seem to transfer that well anymore, especially for weighted graphs. But the actual kind of significant structure in the loss landscape still stays there. But this is not something that you could probably inspect, if not kind of with these scans. Right? And so actually a quantitative way of measuring parameter concentration could be to measure the correlation between these scans as you keep the directions fixed or the point fixed, and you kind of go down higher and higher qubits. And the degree in which the scans correlate in terms of the loss would actually be a quantitative measure for parameter concentration. Just an idea, right? This is something that came out of this project, like just came out, right? Another thing that we observe, especially down here, you can see it, is in the heterogeneous graphs where I've been told that we would actually expect barren plateaus, is we see something that looks like that away from significant features, away from things which are very high or very low in loss, it's getting very flat, right? So it's that's barren plateaus, for example, I would expect to be visualizable also pretty straightforwardly. Essentially, I'm not confident that this is what we're seeing, but this is typically what I would expect barren plateaus to look like. We kind of do expect it in heterogeneous graphs. Right, so this is parameter concentration visually demonstrated in QAOA. Now, as the next algorithm to test, we had QCBM. It's actually quantum circuit bond machine. It's a generative model. I'm sure not many are very familiar with generative models, but the idea is that you're trying to model the probability distribution that underlies available training data, right? So you get training data, and what you're trying to learn is the distribution from which the training data was sampled. And so what we typically do here in QCBM is train on with the so-called KL divergence, which is a distance measure between your current model distribution, which is actually the probability of measuring a given kind of outcome in our wave function. Right, so it's a distance measure between our model and the observed data that we have available. And it goes in with this logarithm of the ratio of probabilities. But that's not so important right now. Right, so we want to study the data dependence, because what we want is to generalize. We want to get this kind of subsample data set and essentially converge to something like that. We're going to learn the distribution that underlies the data. And so we have these differently sampled distributions, and we train on them. And we observe kind of the KL divergent loss. It goes down, right? The training loss, the solid lines, they go down. Here we have the final converged solutions. You can see, yeah, it fills in some gaps. That's good. But what we also have here is the dashed lines. The dashed lines are actually the test loss. Usually we wouldn't have, like in a practical case, we wouldn't have access to that, but this is kind of a toy model, like research, right, topic. So the dashed line is actually the test loss with respect to the true distribution. So this distribution was training on this distribution, like this model was trained on this distribution, but we can also evaluate the distance from here to the true distribution. And that's what the dashed lines are. And we see that if you don't have enough training data, your test loss actually starts to diverge, because at some point, getting closer to the training data doesn't get you close to the true distribution. And that's also a measure of your model, right? That's also a measure of the training data. and how much you have of it. And so we tried to visualize that, and we did that by performing a PCA scan on the collection of these three trajectories. And so doing a PCA scan on these three trajectories starting from the same point. They all start from the same point up here, and up here. And we see them on their respective training loss landscapes. And we see that the 500 sample loss landscape actually correlates quite well with the true distribution landscape. It's just at the end, it's pretty flat down here, and then it's like differences in details start to matter. But generally, these two shapes are pretty similar in the loss landscape. So what that means is our model seems to be good enough for the data, for the task, or we have enough training data that the loss landscape actually seem to correlate, which is good, which is what we want. We want that optimizing on training data brings us closer to the true distribution. Now, if we don't have enough training data, the loss landscape actually looks pretty similar. And in fact, we look at this cross-evaluated kind of projection down here, we see that it's kind of starts to diverge in the true distribution landscape. And so this is kind of a visual demonstration of what it means to be data dependent in QCBM. Now, we also have VQE and another story in noise. But just to give you a quick overview of VQE, we're trying to, for H4 molecule in the rectangular geometry, so for hydrogen atoms that are here, we're comparing two different ansatz of the same family, the unitary coupled cluster family, because we know that the type of ansatz and initial conditions and stuff like that are very important for VQ. And so we're going to visually kind of compare these two ansätze, where KUP is kind of a generalization of UCCSD, where you evolve your wave function under excitation operators in your molecular system, and you have this kind of layered. It's generalized because it also has other excitations that you evolve under, but also layered in this K integer value. And so you expect more expressivity, but it also has been seen to not scale as well. So not mean that because actually the K layered ansatz lacks an initial condition, a good initial guess, it actually hasn't been successful optimizing very large molecules and with very large K. And so we show that KUP is generally quite good. It's generally it seemed to be very good, right? We also kind of show some fancy landscapes behind the this isn't optimization minima trajectory. This is actually the position of the minima in high dimensional space, and doing a PCA scan over that. Right, so each point in here has its energy, but it also has its parameters. That's what we measure here, essentially. And so we see here specifically that each minimum is closer to every other minimum as we stretch the molecule. It's closer to each other than each minimum is wide. Right? So you can kind of confidently initialize kind of in any minimum and kind of get to a good solution. But we also can use the natural elastic band argument between two found solutions, where we start with linear interpolation and kind of go to this sloped down, kind of relaxed, optimized path between minima to show that these minima are very isolated. So you would expect kind of to go, you hope to kind of get low chemical accuracy anywhere between two minima, because that's usually because in classical neural networks that has been associated with trainability. But essentially, there's kind of a whole slew of good solutions. And here it seems to actually be not the case, right? So this is kind of the first indication why with 8 qubits trained with H4, KUP seems quite good. It also seems like its minima are very isolated, as indicated by the natural elastic band, which seems to go to this to the experiments, numerical experiments, which have been done on larger molecules. And finally, stochastic optimization and the effect of shot noise. Just wanted to give you a brief rundown, because here we compare two different optimizers, how it behaves with different number of shots. Right? And so on the left is kind of what you would expect in just regular numerical studies, where you have kind of performance of a given optimizer for a different number of shots, right? So you have the differences between SPSA, which is gradient, stochastic gradient, and the gradient-free evolutionary algorithm. But with visualization, you can actually do PCA on the trajectories of optimization. You can kind of see the character, where with more shots, the gradient, stochastic gradient is getting closer, with less, and with SPSA, well, but with the evolutionary algorithm actually stays very non-local. You get, every time you get a different solution, just distinctly different. And you can also kind of check differences in the loss landscape, but just to cut this short, right? So you can visually inspect kind of the effect of shot noise on the landscape and see that errors are kind of symmetric and unbiased in something like VQE, where you estimate energy over Hamiltonian. But in this QCBM example, where we have the logarithm, actually shot noise gives you huge kind of percentile errors and huge upwards biases in the estimate of loss function, which is maybe for someone, but which is very interesting, very necessary to know when you're optimizing with finite shots in actual quantum computer. So just to wrap this up, and we can, I'm happy to discuss anything after this session. But yeah, I really think that visualization and hopefully ORQVIZ should be one of the many tools that people use to perform their research, right? It's just another tool between theoretical work and numerical work that they can use to approach their problem, right? So here we approached everything visually in a sense that's obviously not necessary in programming optimal, but it's a tool that people may want to use. And some problems like noise effect on landscapes and parameter concentration seem to be very naturally visualized. And so if you happen to work on something like that, visualization might be very helpful for you. And ORQVIZ is here really to help you out and has a lot of helpful functions, gives you a lot of flexibility, but you don't have to overcomplicate. You can just get started, give it a try, let us know what you think. And yeah, with that, I'm out of time and happy to take questions later.
Thank you very much. If anyone has a question, please just unmute yourself and ask.
Yeah, so I have a question. So you comment, Manuel, so you comment briefly on the barren plateau. So did you observe barren plateaus in this numerics, or did you have related plots about them?
Well, we didn't explicitly do these gradient magnitude plots as you increase the circuit depth and qubit number. That's not something that we did. But just looking at these plots, gradients are defined as plus epsilon minus delta, so in a sense, right? From a given point, and that's what we see. Right? So this is really what we would expect barren plateaus to look like. It's like away from a solution or a maximum, or like from significant features, to just not measure plus minus epsilon differences. Right. So, but we didn't rigorously kind of perform these, like the definition of these barren plateaus. So that's what I'm more carefully saying. This is what I would expect barren plateaus to look like. And
yeah, so the people talk about barren plateau, I think, based on the following assumptions. So firstly, it has to be sufficiently random variational assets. Secondly, it has to be sufficiently large amount of qubits. And probably it's hard to numerically have them both at the same time in your current framework.
Yeah, I mean, it depends, right? So the white point, for example, is random, like randomly chosen parameter. But for example, for heterogeneous graphs, the randomness comes in the graph. The problem itself, actually, it being weighted with completely continuous weights, essentially introduces the randomness that would then lead to barren plateaus, even with an Ansatz QA way, which is highly informed. Yeah.
Great.